Alright, in the previous class we have finished with the first two derivation, axial line and equatorial line. In this particular class we are going to discuss about the Gauss law and its application. In order to move forward with the Gauss law and its applications, there are basically three derivations. First we need to know a few points before we start with the derivation. What do we need to know? The first one is the definition of flux. First one is definition of flux, electric flux to be honest. Okay, and what is the definition of electric flux? The equation for this is electric flux is equal to integral of E dot ds. Integral of E dot ds. It's a cyclic integral. We call it a cyclic integral here because for flux we take a closed loop. Okay, so that is the reason behind. So we need to remember this particular equation, and also another way of writing it is summation E dot ds. And obviously be it summation or integral, different textbooks take different symbol. Both of them can be used. Now E dot ds is there, that means we need to take a dot product. So in future when we take this eds, it becomes eds cos theta. It becomes eds cos theta. So this is the first formula that you need to know. The second one is, what does Gauss law say? Gauss law states that the total electric flux over a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. So these two formulas are important to understand the application of Gauss law. If you know these two formulas, easily you can do the derivation. Okay. Apart from this, one more basic from the maths, what you need to know is for a sphere, volume is 4 by 3 pi r cube, a standard formula. Surface area will be, when you differentiate this volume, you get surface area. R cube becomes 3r square, 3 and 3 get cancelled. So what do you get here? 4 pi r square. This will be the surface area. And for a cylinder, because the applications we use, we will be using these two. For the cylinder, the volume is pi r square L, and surface area, when you solve, r square becomes 2r, so it becomes 2 pi rl. So these two formulas you need to be knowing, this one and this one. Surface area for a sphere, surface area for a cylinder, and obviously Gauss law and the definition. With these four basic formulas, let us move forward and start with the derivation. You can have a look before I move forward. You can make a note also. Alright, once you are familiar with the derivations which I have told, the formulas which I have told, sorry, with these formulas, let us move forward to the first derivation, that is the first application of Gauss law. Okay, so let me write down the first application of Gauss law, that is for a charged spherical shell. For a charged spherical shell, what will be the electric field due to a charged spherical shell? We need to find out. Alright, so for this, what do? We need to take a spherical shell first. Let us take a spherical shell, and to that, let us say the positive charges are there all over the place. Let us say it is charged to say capital Q. This will be the center, and let us say this is the radius capital R. Okay, we need to find, due to this charged spherical shell, what is the okay, let us take a little bit closer. At point P, what is the electric field due to this charged spherical shell? This is what we need to find. So how we do it is, the initial explanation also I will tell you. First observe the figure and then we will move forward. Okay, we will consider a charged spherical shell. Okay, I hope this looks like a circle. And yeah, so what did we do? This particular dotted circle that I put, that is actually a Gaussian surface. So to consider to find out the electric field at point P, I need to consider a Gaussian surface in the form of a sphere of radius small r of radius small r, and this particular Gaussian surface is placed such that point P is on the surface, on the you can call the circumference of the sphere. Okay, with this you can write the initial explanation. What is the initial explanation that we can write? I'll just dictate, you can make a note if you want. Consider a charged spherical shell of radius capital R with O as center, let Q be the total charge on the sphere. So this we have defined about the sphere. After this we'll write, consider point P at a distance small r from the center of the sphere where electric field needs to be found. I repeat, consider point P at a distance small r from the center of the sphere where electric field need to be found. So this completes your initial explanation. After this we will tell, consider a Gaussian surface in the form of a sphere of radius small r. Okay? So once you tell that, the whole figure explanation is done. After this what we do is, we consider a small area over here, and area vector will come outside as ds. Okay, small area ds is taken, its area vector ds vector is coming outside. Electric field at this point P is also in the same direction, because all the charges that are there, all the charges here together, they'll act as if the charge at a single point. Because of the positive charge, the if you know the positive charge, all the electric field lines are outward. Yes, so based on that, when you consider point over here, it comes straight outside. Okay, so I hope that is clear. So you are getting ds and vector and electric field in the same direction. So once you have written the figure, once you have written the initial explanation, now we can go to the figure I had given you in the starting of this video itself. We need to know two things. So we start from, by definition of electric flux. By definition of electric flux is equal to integral, cyclic integral of E dot ds, which is equal to cyclic integral of E ds cos theta. Cyclic integral of E ds cos theta. This can be written as integral E ds, because cos theta here is 1, as theta is equal to 0. What is theta? Theta is the angle between E and ds. So ds is here, E is here, both are in the same line, so obviously theta is 0. So cos 0 is 1. So you got the first expression. This can still be written, electric field is uniform, because the charge distribution is uniform, it can be taken out. So you get integral ds. Electric flux is equal to, just a minute, let me rewrite it. Electric flux is equal to E integral ds. Now, but integral ds is nothing but what? Surface area of a sphere. Surface area of sphere, which is equal to 4 pi small r square. 4 pi small r square. Why small? Because whatever we are doing right now is for the outside Gaussian surface. That's why we will take 4 pi small r square. So the final expression becomes flux is equal to, electric flux is equal to E into 4 pi r square. This will be your first equation. Okay, with this let us move forward. The second type we write from Gauss law. Okay, you will write from Gauss law. I can write electric flux is equal to 1 by epsilon naught times the net charge enclosed, here it is capital Q, as we had mentioned in the initial explanation. So this will be our second equation. So from 1 and 2, what is going to happen? The left hand side of 1 is E into 4 pi r square, sorry, right hand side, and here the right hand side is capital Q by epsilon naught. Rearranging, you will get E is equal to 1 by 4 pi epsilon naught Q by small r the whole square. So this is the equation for electric field at a point outside the shell. What we did right now is for the point outside the shell. You can clearly see the point P was taken outside the shell. Okay, shell is here, outside we have taken point P. Okay, another two cases are there that can be used in the MCQs also. If we take in the second case, in the same sphere, if we take on the surface, if you take it on the surface, all you need to do is, our figure was like this, point P was here, center was here. Now if I have to bring point P to on the surface, actually what is happening, small r bahar tak tha, so center to circumference capital R tha. So when you bring point P to the surface, what will happen, small r will be equal to capital R. So you can write small r is equal to capital R, and you need not have to solve everything, you just have to rewrite the expression Q by capital R square this time. Okay, that finishes the second case. And the third case, inside, point is inside the shell. If the point is inside the shell, what will happen? So obviously I used to take something like this now. When you take the sphere this way, okay, after this, if I take from the center, if the point is inside point P, what will happen, Gaussian surface will be inside. Now Gaussian surface, we know from Gauss law that the total electric flux over a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. Enclosed by the surface means in that surface there has to be charges, but we know that shell has charges outside. Right from the starting we are writing the charges on the shell. So if the Gaussian surface is inside, what will happen is nothing is being enclosed by the by that surface. So what will happen, the equation of Gauss law, that is flux is equal to 1 by epsilon naught times Q net charge, this part becomes 0, that's why flux becomes 0, automatically electric field we get 0. So for the third case you don't have to write anything, just have to tell for inside the shell electric field is 0. So I hope you have understood this particular derivation that we have done. Just try to go through once again so that it becomes easier. What and all did we do right from the start, I'll just brush it up. Okay, yes, so let us move forward. Definition of electric field we did first. Electric flux we did, flux is equal to integral EDS, first definition. Then Gauss law, what does it say? Okay, one more thing, when they ask this derivation, always better to state Gauss law. State Gauss law, you get the statement from the textbook. I have also dictated while writing. I have told you the total electric flux over a closed surface is equal to 1 by epsilon naught times the net charge enclosed by the surface. So that you can write. After that Gauss law equation you need to know sphere, volume of a sphere से आएगा surface area, cylinder के volume pi r square L से आएगा, surface area 2 pi r L. आपको याद रखना है these two. You have used this, in the next video we will be using this. After this, charged spherical shell we started. Consider a charged spherical shell of radius capital R, which is charged to the net charge capital Q. Then consider a point P at a distance r, small r, from the center of the charge sphere where electric field needs to be found. So there we considered a Gaussian surface in the form of a sphere of radius small r. After that we took consider a small area ds and pointed out the ds vector. We also pointed the electric field vector. After that our definition started. By definition of flux, integral EDS, then EDS cos theta becomes 1, so EDS बचेगा. आफ्टर दैट E बाहर आएगा क्योंकि कांस्टेंट है, इंटीग्रल DS बनेगा 4 पाई आर स्क्वायर, सो 4 पाई आर स्क्वायर डाल दिया. फ्लक्स इज इक्वल टू E इंटू 4 पाई आर स्क्वायर इज योर फर्स्ट एक्सप्रेशन. इन दिस R मस्ट बी स्मॉल because all that calculation we are doing is for the Gaussian surface. From Gauss law, you write the Gauss law, then you just equate the two equations, you rearrange, you get the equation E is equal to 1 by 4 pi epsilon naught Q by small r square. When it is on the surface case, small r becomes capital R, so small r is replaced as capital R. Inside the shell it is 0. So I hope till here it is clear for each one of you. One small note let me give here itself. Okay, whenever you take a spherical shell, okay, whenever you take a spherical shell, and I am marking the same thing on a graph, okay, so that you understand the graph also, what is happening to the electric field. Okay, inside the shell the electric field is 0, so your graph will be something like this. From here to here it is 0. Okay, after that ऑन द सरफेस से 1/4 q by capital R आ गया, उसके बाद स्मॉल r होता गया, isn't it? So this guy directly goes like this. So this will be the graph. This red line which I have drawn will be the graph for electric field for a thin spherical, hollow spherical shell. I hope this particular topic is clear. In the next video, we will be discussing about the thin long straight wire charged with linear density lambda. Okay, thank you.